Alright, here we go. Day 3, or notes 3 of differential equations. Before I start, two things. One, Harrison, you'll let me know whether or not I was successful in making the volume on this louder. I think I did. And then second, Audrey in class yesterday had the question about, well, where do these differential equations come from? So they come from things like circles, or equations that we have. So let me just remind as way of quick review. If you take the equation of a circle and you do implicit differentiation of the equation of a circle, then you will end up with, right, so I'm going to go through and take the derivative of each one of these terms, the two on the left and the one on the right. This is going to give me 2x plus 2y, and because I'm taking the derivative with respect to x, I follow the chain rule, and then this becomes dy dx, which is equal to 0. Subtract 2x from both sides, divide both sides by 2y, I will end up with dy dx equals negative x over y after reducing the fraction. And this derivative gives us a pattern for the slopes at any given point on the circle. So if I want to find the derivative of at the point right here, which looks like the x-coordinate and the y-coordinate are equal, then the slope is going to be close to 1, and it's going to be negative. If I'm over here, x-coordinate and the y-coordinate have the same magnitude, I'm going to end up with a positive slope. If I'm here and I have a very large x-coordinate but a small y-coordinate, I'm going to get a very steep slope, and it's going to be positive because I'm down below the x-axis, so I have a negative y-coordinate and a positive x-coordinate. So this is giving us the pattern of the slopes around a circle. The last 2 days, what we've done is we've started, excuse me just 1 second. Last 2 days we have started with, excuse me, just 2 seconds. Now I've got it. The last 2 days we've started with this and asked you to find the parent function. Okay, so here we go. Moving on. So differential equations, day 3. You might want to pause this and take a second to read that portion first. Okay. Having read that, you're probably wondering what this right here means. When we give the change in population, we look at the rate that the population is changing. A lot of times we give dp dt is the rate that the population is changing over time. A lot of time you see that in terms of, maybe something like this. 3t, where the rate after 1 second is going to be is 3, the rate after 2 seconds would be 6, the rate after 10 seconds would be 30. And then sometimes you'll see that it's something in terms of p, which just simply means that you would have perhaps 3p. So the larger the population, the larger the rate. Population growth is directly proportional. So just a quick reminder that directly proportional, if two quantities are directly proportional, they have this relationship. The one changes with the other, and there's some sort of constant k. So here, example 1, let's do example 1 in purple. So we have a rabbit island. Its population is growing continuously at 2% per year. So this is 2% of the population. So when the population is 5,000 bunnies, the rate is 2% of the 5,000 bunnies, which is, right, so 5,000 times, that's a times, sorry, 0.02. So then the rate of growth is 100 bunnies per year. But if the current population is 5,100 bunnies, 2% of 5,100 bunnies is going to be slightly larger than that. Again, that's an x, 0.02. And you're going to get 102 bunnies per year is going to be the rate of growth. Okay, so now moving on to question C. Question C is asking us to come up with a function that'll tell us, if I give you the time, how many bunnies are there? And we're going to use the rate, the 2% growth per year, to help us come up with this equation. So we start by writing the differential equation. Right? What's the change in the bunny population given a change in the time? And we know that the bunny population, the change in the bunny population, is directly proportional to p. So the differential looks like this. And then, just like we've been doing the last couple days, we're going to take all of the stuff pertaining to p, put it on one side, all of the stuff pertaining to t, and putting it on the other side, which will look like this. And then we're going to integrate both sides of the equation. Which will give us this. And again, notice that when you take the integral here, since this is an indefinite integral, we should end up with a plus c over here. We have the plus c over here. The plus c that was over here ends up over on this side. And then the last thing to note is that this is the natural log of the absolute value of p, but I'm not going to bother putting the absolute value of p because I know that p will always be positive. There is some scenario one could imagine where p would be negative, but that's not in any kind of world that I know of. Next step here is to take, and we want to get rid of the natural log. So if we think of this being an exponent and this being an exponent, and we make on the left side e to the exponent natural log of p, and on the right side we do e to the natural log of 0.02 t plus c. And then we simplify this, and again we're going to end up over here with a constant. Looks like this. And if you're confused about where this constant a came from, then ask someone. Moving, the next step is to then take the known value. We know that at time 0, so we're going to plug in 0 right here. So we're going to end up plugging in 0 here. We know at time 0 that we have 200 bunnies, that our population is 200. So then we end up plugging in right here. 200, and then we're going to solve this for the constant a, which then looks like the following. So we end up with the constant a equaling 200, plugging that back in, then we get the equation that describes how the population, or describes the population given a time t as 200 e to the 0.02 t, which should look very much like something you've seen before, where the population hold on, excuse me, which looks a whole lot like the compound interest problem that you did in pre-calculus, where the total amount of money you have in your bank account is PERT, the principal times e raised to the rate times t, which is what the form is here. And on to the last problem, where we want to determine when it is that there are 500 bunnies. And we're just simply going to use the equation here that describes how many bunnies there are at a given point in time to figure out when it is that we have, at what point in time we have 500 bunnies. So I will just kind of walk through that quickly here. Total amount of bunnies is 500, and then the rest of the equation is just as is written up over here, and then we're going to divide both sides by 200. Then we're going to take the natural log of both sides, natural log of the left, natural log of the right, which is going to get us that the natural log of 2.5 is equal to 0.02 t. We divide both sides by 0.02, and we get that after approximately 45.8 years, the bunny population will be up to 500 bunnies.